In this video, I'm going to talk about continuous distributions, and in particular, the uniform probability distribution. Before we get into a continuous distribution, let's just remind ourselves a little bit about what a probability distribution is. What we want to do is describe, using some math and some graphs, how likely it is that something happens. And what we're talking about here are distributions where the outcome of a random event is something that is a number. And so a continuous uniform distribution is a probability distribution where the outcomes are numbers, and the word continuous here means that the number that can happen is any numeric value in some range of values. That's contrasted with the idea of a discrete distribution. Discrete distribution is one where the outcomes are only certain values with gaps in between. My favorite example that really highlights the difference between these two is if a discrete distribution is your shoe size, then a continuous distribution that's related would be your foot's length in either inches or centimeters. So continuous would be the foot length. So the next person who walks through the door, we could do one of two things. We could either ask them what their shoe size is. Let's think about what the possible outcomes for shoe size would be. Well, in the United States, shoe sizes are usually something like 1 or 1.5, 2, 2.5, 3, etc. And there doesn't need to be any upper limit on what the shoe size could be, but this is discrete because there are only certain little points where the probabilities could exist. There's no such thing as having a shoe size of 2.1 or 2.33333333. Only probabilities make sense accumulating on these little fixed points here with big gaps in between that are not possible. However, let's try to list the possibilities for foot length. Well, maybe the smallest a person's foot could be might be 1 inch. Okay, suppose that's the smallest. Now let's list the next possible foot length. Well, let's suppose the next possible foot length might be 1.1 inches. There's a problem with what we just did. That's not the next possible length. There is no next possible length. And anytime you write down two numbers, there's an infinite number of possibilities in between here, between 1 and 1.1, that we've left out. There's 1.0001 and 1.000000003964.2. So the thing about a continuous distribution is that there are, in math we call it an uncountably infinite number of possibilities. How is that different from infinite? Well, there could be an infinite number of possible shoe sizes, right? We could go from 3, 3.5, 4, and then 1,000 and 1,000,000 and 1,000,000,000. There's no upper limit to what a possible shoe size could be, but there are gaps, right? Continuous means there are no gaps, at least in some range. So we could say, well, foot length could be any number between a minimum of 1 and a maximum of, I don't know, a mile. But any number in there is theoretically possible. So when you talk about things like lengths or temperatures or weights, we're talking about things that are continuous here, not discrete. So now that I've taken a long time to introduce the concept, let's do the example of looking at a continuous uniform. It's the simplest continuous distribution that you can talk about. So let's erase this stuff here and let's talk about an example distribution. Now the one I always like to start off with, just to get us our feet wet, is to look at a specific example let's suppose that we were looking at doing something random, where the outcome is a random number, and it's continuous. Let's suppose we wanted to go outside and measure how much gasoline is left in the tank of a car right now. So there's a particular car outside, and let's suppose that this car has a minimum amount of gas that could be in the tank. Might be 0, right? It can be empty, but it can't be negative. And the maximum amount of gasoline that could be in this car's tank might be something like, 16 gallons. So any number in between there, if we were to empty all the gasoline out and measure it very accurately, precisely, then any volume between 0 and 16 gallons is possible. I assert that it makes sense to think about there being an equal amount of probability. If we were to make a graph of what we expect the results to be, if we were to go measure the amount of gasoline every day for a year that's left in this tank, that the probability of being at any point along this length would be roughly equal. So if we were to make a histogram of our results, the bars of the histogram would all have basically the same height. That's what I'm trying to convey by this picture. So theoretically, equal probability along each point. Now, let me ask a couple of questions here to get us started. On average, how well, instead of talking about how likely it is, well, now let's start there. On average, how likely do you think it would be that we would be somewhere more than half a tank, say anywhere in this region up here? Well, about 50%. That just makes sense, right? So here's half a tank. What's the probability we'd be more than half a tank? Half the time. Half the time we'd be less than half a tank. That kind of makes sense too. Now, if we were talking about this probability distribution, when we talk about probability distributions, often we're interested in knowing what the mean, mu, or sometimes we call it the expected value of this distribution. What is the expected value? In other words, on average, when we go check this gas tank, how much do we think there should be in it on average? Well, half a tank, basically, right? What is that average? What is that half a tank? Well, it's if the minimum's 0 and the maximum is 16, then it makes sense that the average should be 8. It just makes common sense. Now, how would we do that mathematically? Well, what we're really doing here is we're finding the midpoint between the lowest and the highest number, the halfway point. And that midpoint is just basically looking at the average of the lowest and the highest number. In general, when we look at uniform distributions, we call the lowest number that's possible little a, and the highest number possible little b, so that we can make some formulas to describe what's going on. And the formula for the average is simply a plus b over 2. It's just the average of those two numbers. Now, let's ask a couple of other questions here. Thought question. What is the probability that there is exactly 8 gallons in that gas tank right now? Exactly 8 gallons. So we go, we look at the car, we empty all the gas out of the gas tank, we measure it precisely, and it's exactly 8.0000 and an infinite number of zeros. Maybe you see where I'm going with this now. Not 8.000001 and not 7.999999999, but precisely 8 with roughly an infinite number, basically an infinite number of zeros after it. What is that probability? Well, the probability is going to be 0. Now that doesn't make much sense when you first think about it, but let me try to convince you that this has to be true. What if the probability wasn't 0? What if the probability was some number? even as as small a number as we can imagine, let's suppose that the probability was something like, oh, say the probability that X equals 8 gallons exactly. Suppose, just for a minute, that that was 0.0000, something tiny, 1. Here's the problem with making that assumption. Because there are an uncountably infinite number of possibilities here of what the possible answer could be, if we're assuming that everything is equally likely and that everything has an equal probability of some number, 0.000001, then all we would have to do is add up, let's see, 10, 100, 1,000, 10,000, 100,000, 10 million of those things, 10 million possibilities, and it would be easy to come up with 10 million of them, just say between 0 and 0.1. We're going to start violating some probability laws when we do that. So we can't assume that there's any probability of one particular number. Instead, what we're forced to do is what we've already done. And that is to ask the question, which does make sense, what's the probability that the amount of gas is between two numbers, between 8 and 16? Well, that's 50%. We can do that. But we can't analyze the probability of it just being equal to one exact number. It's so infinitely improbable that we hit one exact number out of an infinite number that it's not going to happen. So we just can't do that kind of calculation. We're always going to assume that we're talking about the probability of being between two numbers. Now, how do we do this in general? It makes sense to say that since between 8 and 16 is half of the possibilities, that probability is a half. Easy enough. We can do that. But what if I asked you a slightly harder question, like, what is the probability that the amount of gas, we'll just call that X, is something between, let's say, 0 and 1.5. How would we answer that kind of question? Well, first I always like to draw a little picture of what it is we're talking about here. So between 0 and 1.5 is going to put us right here. We're looking for that probability between those 2 points. It certainly can be done, but what we want to do is find an easy way to do that. And here's the method that we use. We say, well, look, what we have drawn here is a rectangle. And we know how to find the area of a rectangle. So what we want to do is say, look, let's assume that the area of the whole rectangle here is 1, because when we add up all the probabilities, they should sum to 1. So here's the thought question. If the base of this rectangle is 16, what must the height of the rectangle be over here so that the area of the rectangle is 1? Well, just think, what's the area of a rectangle? What's the formula for that? Well, it's base, which is 16, times height. Well, what could we multiply 16 times to get 1? Well, the answer turns out to be the reciprocal, just 1 over 16, right? So 1 over the length, 1 over the base of that rectangle. In general, what we call this, just for a shorthand, is f of x. Just like when you're graphing a function, how high is the function? Well, that's f of x. And that's always going to be the same height in this example. Now, in general, this gives us our second formula. When you're trying to calculate probabilities, the height of this rectangle is going to be 1 over the base of the rectangle, basically. And then what that allows us to do is to calculate probabilities for any region here just by calculating the area of the smaller rectangle. So we can calculate the area of this smaller purple shaded rectangle here and just say, well, the probability is going to be equal to that smaller base, 1.5, the distance between 0 and 1.5, times 1/16. And so what that would give us is, let me see on the calculator here real quickly, I get 0.09375. So a little more than a 9% chance, okay? Now, in general, how do we do this? Well, the formula in general for this f of x thing is simply 1 over b minus a. And the b minus a just gives you how long is the base of the rectangle, and the 1 over just tells us, you know, it's the reciprocal of that, or the inverse of that, okay? And so we can use this to answer probability questions. Find the height, find the base of the section of the rectangle, and just calculate that smaller area. So we're basically asking what proportion of the whole area is this part between 0 and 1.5 in relation to the whole area, which has to be 1, since all the probabilities have to add up to 1, or 100%. Okay? Now, the last kind of thing that you want to be able to do with a continuous uniform distribution, that's a very common kind of question, is to ask what is the variance and the standard deviation for a particular uniform distribution. And let me just give you the formula here. And what I'm going to do at this point in the video is I'm going to link to another video that derives this formula for you, or shows you where this formula comes from. So let me just write it down and take it as given that this is what the formula is for the variance. And if you want to know, so the variance of x for a uniform distribution is take the highest number, b, subtract the lowest number, a, and square it, and then divide what you get by 12. Divide what you get by 12. As I said, I'm going to have another video showing where that comes from. The question always is, why 12? Where'd the 12 come from? I'll make another video showing that, and I'll link to it here. So let's just calculate this to see what it tells us really quickly. And so the variance here would be b is 16, a is 0. So it's basically going to be, for this example, 16 squared over 12. And so that's going to give us 21.333. And what does that mean? Well, variances really don't mean much. That's the way I interpret them. The bigger the variance, the more spread out the data or the results are going to be. But the 21.33 doesn't mean much. What we want to do is take the square root of that, and then we can start trying to interpret it. So here, the standard deviation, the square root of the 21.33, is about 4.6, or 4.62 roughly. What does that mean? Well, just like any standard deviation, we can interpret that to mean, let me clean this up a little bit here, that if we start at the mean and we go up, let me erase some of this other stuff because it's getting a little junky here. If we go above the mean about 4.62, that's going to take us to a number like 12.62. And we go down, let me erase this too. And we go down 8 minus 4.62. That's going to take us to 3.38, I believe. That gives us kind of the most common range of values. Most of the data will be there, or most of the time, this is what we're going to see. Will be between 3.38 and 12.62. So a standard deviation is a common distance that numbers will be away from the mean. What does common mean in this case for a uniform distribution? Well, all we have to do is calculate that probability. Let's calculate the area of the little green rectangle there. So the probability that x will be between 3.38 and 12.62 is, well, the distance between those numbers is basically 2 times the standard deviation, right? Because it's 4.62 over here, 4.62 over there. So the difference between those two numbers is going to be 9.24, I believe. 9.24. times 1/16. And what we're going to get is 9.24. Let me verify that number here. 4.62 times 2 equals, 9.24 times 16, divided by 16 times 1/16, 0.5775. 0.5775. And if you're familiar with the empirical rule is for distributions that are bell-shaped, like this. Let me draw a bell shape over top of this uniform distribution. A bell-shaped distribution is not limited to be between two numbers. I mean, technically a bell-shaped distribution keeps going on to positive infinity and down to negative infinity, but majority of the area of a bell-shaped distribution would be in here. And you see the difference between the shape of a bell-shaped distribution, and what this bell-shaped distribution would mean is that there's a lot of area in the middle and not as much on the ends. And the empirical rule says that if your data has a bell-shaped distribution, not like a flat box, that you'd have about 68% of your probability, or 68% of your data within one standard deviation. With this flattened distribution, we only have about 58% of the probability, or 58% of the data would be within one standard deviation. And it turns out that for any uniform distribution, if you calculate the variance and you calculate the standard deviation, and you look at this range within plus or minus one standard deviation, there will always be 57.75% of the data between those two numbers. That's just one of those constant things about uniform distribution. So that's basically all you need to know about a uniform distribution. And as I said, if you want to know where this 12 comes from, click on the link and I'll show you. But it's always 12 for this variance formula for a uniform distribution. This is Berkey Academy signing out. As always, if you have questions, leave them in the comment section below. Good luck with your studies.